Hello, all of you. I'm Ashish Vajpayee. Yeah, I am taking PMRF live session today for week 3. Yes, good evening, all of you. I'm waiting for others to join for 5 minutes or 2 minutes maybe, and then I'll start. If you have any question, you can ask. Start asking questions. Today, I think there's very less. Let's wait for 2 minutes to others to join. So my idea is today I'll be explaining about the basic strategies of CFD. How can you tackle the problem and start writing code about it. And later I will explain about writing codes, because from next week assignments you are supposed to give some kind of executables for the assignment submission, and your problem should be matching in the nearby numbers to the answers which are given in the assignments. So how is class going on? Are you understanding? Okay, I want to ask that you guys are able to get the class notes there in the drive, because I have seen a lot of requests. No, not assignment 1. That is over. Assignment 1 is over. Already data is gone. 2 is also over. So I think from week 4 you need to give the MATLAB solutions or any executable you want to submit. It's okay. If you have any question, you can turn on your audio and ask. Shubham? Sanatha? Anyone? Okay, I'll start. Okay. I'm waiting for you guys to ask some questions, if there is some, for at least 10 minutes I should, I think. Because class is just now started, so you can ask your questions. But I think it's downloadable link. I shared the downloadable link. So why you need access? The access is for editing. Do you guys need to edit that? So let me check also. Let me check the shared. Madhuri, I am not able to understand your question actually. For which you need to tell me the context. Which thing you want to delete in MATLAB? Connected layers of network. Which network? Are you talking about discretization? See, no, I'm not getting your question. You need to explain it more, your question. Your question is how to delete the fully connected layer of the network in MATLAB. What does this mean? I don't know. Okay, you are not able to open that folder. Fine. Let me check again. Shubham, can you check now? I did that given, and let me know if you are able to. Nobody is having question today. So you can contact me on email, I think. That will be better because right now I'm not getting your question. In which context you are talking. So question number 7 Week 2 should be Week 2. Okay, let me check. So Preeti Pant is asking about question number 7 of week 2. I'm checking that and I will let you know. So there's some correction she's asking for. Let me check it. I'm checking the questions right now. Week 2. So what's the problem there? In this answer of question 7, week 2 assignment should be none of these. So equal to A for the parabolic. But B square minus 4AC is equal to 0. That's the equation for parabolic. Yeah, B square minus 4AC is 0. There it is showing. As I have also told you in the last class that it should not be none of the above. The question is PD is said to be parabolic partial differential equation if it satisfies. So this satisfies B square minus 4AC, then only it's is equal to 0, then only it's called parabolic. So what's the doubt there? Why you want to put none of these? Question C. Yes, sir, but I think it was a misprint. C is equal to A as it is a repeating G. Yeah, it's a misprint. Yeah, you are correct. Okay, but I think it was understandable. You are correct that if it is misprint, then it should be none of the above, but accepted answers is C only. Yeah, you are correct, but I understand your doubt. Yeah, VP. I think this is from the NVTL team side. So this mistake I will raise, and so what you can do is you can mail me about your this done, and I will raise that, or you can mail NPTEL team. That will also come to me, and I will take care of that. If it can increase the marks, I will increase. Yeah, you need to mail NPTEL team. Like there is a discussion forum, in that you raise this. There is a discussion forum. Yeah, for Madhuri, yeah, I'll give. Yeah, that MATLAB question you can ask me on this. But for Preeti, you need to tell me on a discussion forum, because on discussion forum we discuss all the doubts. Others? Yes, Apurva, I will help. Currently, like I will go step by step, but yeah, that will come I think in the next week. The 2D, PD coding part. For sure, next week I will cover that. Yeah, loops. It's concatenated loops which are there for different coordinates. Means you need to take one loop under another loop, and so that I will tell, and how to march in time. That marching is also inside that loop. It will happen. Time matching basically it is called. So Apur, can you tell me where exactly you are facing the problem and loop? Okay, how to start with MATLAB, any problem to solve? MATLAB, any problem to solve? First, I think yeah, I know. You guys just started with MATLAB. So this week four assignment is MATLAB based. So there, I think what you can do is start by writing first. Like you need to have some idea of coding and MATLAB basically. So you can start writing some basic codes. Like if you want to apply loops, can you write a code for writing 1,000 numbers or just basic codes in a loop? And do you know the difference between while loop and for loop? Because for me it's very difficult to cover those things in the advanced CFD courses. So yeah, if you ask a specific doubt, that like suppose Apurva ask his doubt about like applying loops in the code, he don't know how to apply. So yeah, that I will try to cover that in the mostly in the next week session. It will be totally MATLAB based next session. So today I will tell about the basic strategies, how to tackle a problem, so that you'll be able to discretize the problem or just understand the problem. So first thing is in CFD you need to understand the problem, what exactly is they are asking for. Next thing is how you are discretizing the domain. And domain creation first thing, and then discretizing of the domain. Then which equations to solve, and another is boundary conditions, initial conditions. After that, some post-processing part is there. So that I think I should cover first before directly going into the code. Code is just implementing those equations into some kind of computational framework. I hope everybody is getting it. Other questions? So let me tell you the basic strategy. What a strategy one should follow to cover a CFD. So you have given a problem. Suppose in week 4 there is a problem today uploaded. Just a second. हेलो हेलो हाँ मैं हाँ बाद में करता हूँ. Can we, Sony Atwal is asking about can we define any equation? Okay, before that, Samantha is asking about how to apply Dirichlet and Neumann boundary conditions in the context of CFD software. So yeah, these are just names, Dirichlet and Neumann boundary conditions basically. So there, uh, whenever you are applying, suppose, okay, I'll tell. So suppose this is the domain of CFT, which a plate at a temperature, and you need to provide some temperature here in the boundary, which is a constant temperature. Okay. And another problem is in which you have this dt over dy as a constant. So in your CFD code, you have to just put it like this, like t is equal to constant or dt over dy is equal to constant. So these are two type of boundary conditions. In this one of the boundary condition you need to apply, whichever is satisfying for that problem. So there is no such thing like during the code coding part, you don't need to like think of this is the Dirichlet boundary condition or Neumann boundary condition. You just need to think what is the process happening there. Is it the constant thing happening? Is it the like there is this suppose dt over dy is a constant there or not, whichever is the thing, or there can be a mixed boundary conditions also. So there you directly think about these things. Sony is asking about can we define any equations in Fourier series distribution, or can we define any equation in Fourier series distribution? No. It is applicable for all the equations. Yes. So my Sanatha, is it clear about Dirichlet and Neumann boundary condition? Okay. So do you guys understand the Dirichlet? Actually, what is Dirichlet in this? Which one is Dirichlet or which one is Neumann? Anyone can tell me? Dirichlet is basically first type of boundary condition, which is this: t is equal to constant. T is equal to constant, kind of. Yeah. And this is Neumann boundary conditions. Yeah. Suppose you have given a problem. Okay, others are not asking questions, so let me start. So you have to divide the domain. I'm also writing so that I will give this notes to you. So why we create mesh? Anyone can answer? Do you know why we create mesh? What is mesh? What is discretization? Any of you know? Suppose this is a domain given to you. Why you will discretize it? Discretization means putting it into some more parts, cracking it down to smaller part every time. Why we do? No. First is not to discretize the equation. Mesh generation is not for discretizing the equation. Yeah, small domains. Yeah, is saying that small domains. Yes, why we create small domains? That's question is. Yeah, you are correct. Purvi is saying to find the flow parameters at the nodes. Okay. One thing is that we can't find a continuous solution at all the points because it's so we will solve at small in the small domain at different points. We will solve that equation, and for that we need discretization, and for every point in the discretized domain we will get the solutions. So that is the reason why we are discretizing. Then comes converting our governing equation into simple equation. Simple equations means differential equations for each subdomain. So as I said that we need to solve for each subdomain. This is called as somebody said, yeah, Sony said, discretize the equation. So here we are discretizing it. So this is the second step for any CFT problem, and let's come to the then apply boundary conditions and so this will form the basis for next assignment basically. So what we will do is, suppose now I am again generating the domain. Then I have discretized the domain. First step is discretizing or the mesh generation. Then I will discretize the equation, and I will apply the boundary conditions at all the boundaries. So boundary conditions will be applied, initial conditions of the solution will be applied, and then we will solve the equation at every domain. So for this domain, suppose I have solved equation, again for this domain I will solve. So for every subdomain I have to solve the equation and find out the different parameters at the nodes. Now, this is for one time, single time. uh, Next I need to solve it for next time, which is called time marching. Okay, so this is suppose for 1 second, 0 second I have solved, then my flow will go to 1 second, so I'll solve for first second. So yeah, so that I will write here, continue. Transient problem here. If it is not, obviously, if it is not steady state problem, then only we need to do for time. And after that, whenever we will get the results, we have to do analysis. This is called post processing. Till now, any problem? So I'll just take 5 minutes or 2 minutes break. If you guys need break, you can also take. Every half an hour I'll give 2 minutes break. You can take it if you want. Everyone there? Yeah. So this is the live session. Actually, you guys need to ask a lot of questions. For that, I am here for. I can't just teach. It's because my health condition is also not fine. So if you ask question, I'll answer. Till then, I will just do some initial basic steps of safety problem, how to tackle that. So develop a, so if you have given any problem, any physical problem, if you are given, the first you need to know about the which mathematical model one should develop to tackle that problem. Like right now, so suppose a heat transfer problem is given, then you need to apply the heat conduction equation or heat convection equation or energy equation. Nobody is asking question now. So simplify the problem. Then you need to simplify the problem. By making appropriate. Oh, what happened? Assumptions. Suppose there is an assumption of incompressible flow. So you will not apply the compressible equation there because it will enhance the complexity of the problem or complexity of the numerical scheme, and it will take more time to solve it. 2D. So if you are having a 3D domain, then it will take more time to solve that equation for that 3D domain, but for the 2D domain it's a bit easy. So we need to then develop a governing equation. Mass, as I already told that there are three types of conservation equation here: mass, momentum, and energy. And then we need to define the fluid properties. In this also, if you have doubt, you can ask. Then providing initial and boundary condition. So this is a whole whole code generation part. These are the steps you need to follow for generation of that code. Grid generation. No questions from your side. Just listen to just look at it carefully, all the things like this. These are the things you need to give in that code. I will end today early because I think participation is very less. So what I will do is for some problems I will record some part of it and I will add it in this lecture only. So it will be a big YouTube video that will be provided to you in that forum, and then you can access that for solving that problem. Schemes are for discretization of the equation, Sony, and finding out that whenever you are after discretization, when you are solving so sometimes you need pressure also, sometimes you need temperature. So suppose you need pressure and you are solving a fluid flow problem, then in that there is a problem because pressure is not discretized in the time. So what happens, we need to have some kind of algorithm to find that pressure. So one of the algorithm is called simple algorithm, semi-implicit method for pressure linked equation. So there what we will do is so I will write that equation, Navier-Stokes equation. So this is here, this term, and this is here, this term, and P is there. Okay. So these all the terms in the left hand sides are actually it is discretized in time, and UVW is not discretized, and it is discretized in space. So it is not discretized in time, and the pressure is actually, there is no time term here. Del over del T is not there in pressure. So when we march in time, suppose this is T is equal to 0 and this is equal to T is equal to 1. When we march in time, what happens? The pressure is not changing. We don't know the pressure at the next time step by that discretization. So for that we need algorithm to find that. So one of the algorithm is simple algorithm, Pimple algorithms, and other algorithms, so that we can find this kind of pressure thing. So schemes are used there, and if you are asking about upbinding scheme and central difference scheme, those are used while we solve the equations. So in this step. Very less participation from your side. Only some guys are, some of you are participating. Okay, how will we decide which scheme to use? Okay, that's a very good question. So it depends. Suppose you are having a second order equation, then it depends on which type of like how much stability you want, how much one thing is stability, another thing is accuracy, and which scheme is applicable there. So there are schemes which are not applicable at every place. These are the things. Suppose you have applied the winding scheme in some problem, but Neumann, you have understood about von Neumann stability criteria. It should be theorem. Sanada, I didn't understand your question. Theorem. Which theorem is? So I was telling about schemes. So schemes. Okay, the question will decide which scheme. Yeah. Suppose you are applying a winding scheme or down a center difference scheme. So then you need to check the stability criteria, CFL number there, and if it is satisfying that, then it is fine. If it is not satisfying, then you need to change that. So yeah, that's a criteria for deciding, and later I think we will discuss that for sure. So you have to develop it by something by experience also. So now I will just tell you about discretization. What we will do in the discretization is the divide of entire domain into a number of subdomains. So which is called as control volume or sometimes element. In 1D it is called element. In if you are applying the volume approach, it is called control volume. Each of which represent one or more discretized points. Yeah, as I told you, simplify the governing equation into the simple form, and a system of algebraic equations are need to be solved for obtain the required variables. So yeah, I should. I will end it soon today because I will upload 1 hour lecture there in YouTube more. It will be 2 hour lecture, but now I am not feeling good, so if you have questions, then I can answer. Yeah, I don't have. Yeah, ask. Question 5 in assignment 3. Okay. Second assignment. Okay. Yeah, I'll share my screen. Sure. The date is over for this assignment. Okay. Now you can see my screen. My screen is visible. Third question. Hmm. Mm-hmm. Mm-hmm. Yeah. Uh, yeah. Mm-hmm. Okay. Okay. I will tell from the. I think there is some error in this answer. Should be less than one. Why you guys are not raising this out in a discussion forum? Because like I don't have control over these by submission. You raised it? Okay. I didn't saw it actually. Okay, so maybe I'll see today and reply to you later. Uh, okay. Okay. Yeah, I think there is some mistake in that question. I'll look for it. I think there is two mistakes. One another person also pointed out one mistake. I'll look for it. You guys just send me on that discussion forum. You just raise that question. Okay, because yeah, you'll lose your marks based on that. Yeah. Yeah, I'll look for it. Others? So let me see like if I can see your question in the discussion forum. Okay, Shri Dattam. Okay. Okay, just now I have seen. I'll try. Okay. Okay. Yeah, yeah, understood. Now I don't. You don't need to do anything. Okay, okay. I just now saw it because it's from 4:15 p.m. I think. Today you sent it. Oh, 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 then it's late actually. August 10. Yesterday. Fine, fine. I'll. Okay, I'll. It's a 2 hour session. I will upload 1 hour MATLAB video there in YouTube that you can watch. Right now, I'm not feeling good, so I'm currently stopping it. You guys can take help from that MATLAB video for the next assignment. Right now, like I can tackle only the problems you are getting. I can't teach right now. So, yeah, I'm ready to answer. Okay, let me stop it and upload the video later. Bye. If you guys have question, then you can post it in discussion forum and even email me there. And MATLAB video will help you for sure. That I will take care. Some initial coding problems I will take care. Tomorrow I think I will upload it. Today I'm not feeling very nice, so yeah, I can't tackle that because yeah, it's a bit intense to teach. So tomorrow I will upload it. Thank you all of you.
Hello, all of you. I'm Ashish Bajpai from IIT Kanpur, and today is the Week 8 live discussion class. And I'm taking this computational fluid dynamics and heat transfer live discussion sessions. So, here, if you have any doubt, you can tell me, you can let me know, and I will try to answer it. And today, like in the last class, we have discussed about the TDMA algorithm, which is diagonal matrix algorithm, and that was one of the part of that direct method. And today we will discuss other iterative methods like Jacobi method and Gauss-Seidel method. And along with that, we will also cover uh, line by line TDMA, how to do the equation solving in line by line TDMA. Along with that, I will also introduce you to the topic we need to cover is finite volume method in from the next class, and then we will learn about the um, how to solve the equations for finite volume method, which is solving of integral equations and the finite volume. And uh, when we solve it, then we will also discuss about the different type of algorithms by which we can solve or we can uh, solve those problems of finite volume method by finite volume method, like simple algorithm, mac algorithm, simpler, and over different type of algorithm which I have discussed in the week 1. Uh, okay, let me just search it. Uh, uh, so this is my first. This is the from the this class we will cover this Jacobi method, then Jacobi method, then Gauss-Seidel method, and line by line TDMA. previous class we have discussed about the direct method, which is TDMA, diagonal matrix algorithm. Now we will discuss about the iterative method to solve the solution of the linear algebraic equation, which is very important actually. So this is the one of the fundamentals which everyone needs to know for solving any of the problems related to computational fluid dynamics. Then and from this class, I will start the finite volume method. This I will discuss something about 1D study diffusion. Next class, I will cover it totally, finite volume method. Then after that, I will cover this affinity scheme and different finite volume method for convection diffusion problems. Then how to solve the Navier-Stokes equation using that finite volume method, and just like that, and we will just conclude our classes after that. So today in the iterative, uh, let's let me check it. Okay. So iterative methods here. Why we need iterative method? We are using that. We were using that TDMA method, which was easy for 1D, because what we were doing in those TDMA method is first we were solving in this right direction in the forward manner, and then we will again go in a backward manner, which is in the reverse direction. So we will first solve in this direction and then in the reverse direction. So solving that, suppose there is a domain, 1D domain, where I have divided it into the 100 parts. So 100 parts, it is easy to do it in. The matrix which I will be having is easier to inverse it, and if I am solving it by TDMA, it is comparatively less computational expensive when I will do it by TDMA as compared to other methods. So I can do it. But when I come to 2D method, 2D, what happens? This 100 division will become 100 into 100 division, which will be 10 to the power 4 division. So I have to solve 10 to the power 4 equations, and for that, again applying this TDMA is very difficult. And again, let me come to the 3D part. 3D, it will be 100 into 100 into 100, which will be 1 million points. 1 million points. And it is next, like, if it is taking just 1 second for one iteration, one solution, then it will be exponentially higher time to solve the 3D type of problems in with the TDMA. So let us come to the some other solutions of the equations by which we can solve uh, uh, 2D and 3D problems, which are iterative methods. So I have written it suitable for 2D and 3D problems. The 2D and 3D problems are having uh, different number of equations as per their grid uh, grid formation, or as per their number of equations it is using. So TDMA cannot be used, which I discussed directly for 2D number of due to number of grid points, 2D and 3D problems. Other direct methods such as Gaussian eliminations are slow in that. So uh, if I okay. Okay. So for TDMA cannot be directly used, which I was discussing, and for 2D and 3D problem due to like exponentially higher number of grid points, and time will be exponentially higher actually. Grid points and equations we can handle, but time uh, it will be uh, humongous time, which it will be taking like some years or something. for solving some 2D or 3D problem by TDMA method. So let's come to the and for the Gaussian elimination, these methods are very slow. So same time dependency will be there. So let's come to the some other solution of those equations, some other method to solve those equations. One of the method is Jacobi method. Jacobi method is very simple, you can say. It's an iterative method in which we will just iterate the equation by taking some initial values and by again and again iterating that equation by the previous values of the variables. We Okay, sir, it is not audible. Okay, sorry. Okay.
Hello. Now is it audible? Or can you tell me? Because it is very important for me. Am I audible now?
Am I audible, Arun?
Oh, thank you,
Oh, thank you so much. Thank you so much. Okay. So let's discuss this again, which I was discussing. So I was discussing about. Please tell me whenever it is required. So I was discussing about iterative methods. Iterative methods which are suitable for 2D and 3D problems. Um, okay, so like, do you know about the TDMA algorithm which we have discussed in the last class? This TDMA. Just let me know. Okay. So TDMA, why we have used for 1D problems there, but when we try to apply TDMA, time diagonal matrix algorithm for 2D and 3D problem, there will be the problem of computation. So just a second. I'll just Okay, so there will be a problem of computation because of the huge grid points in that. Number of grid points will be higher, so the number of equation for solving by TDMA will be very high, and the steps will be like those forward elimination and the backward elimination will be very huge in that. Like I discussed it previously also. Suppose 100 grid points in the 1D domain, so we can solve it, but in the 2D domain when we go, it will be 10 to the power 4 number of grid points, and when we go to the 3D domain, it will be 10 to the power 6, which is 1 million grid points, and it will take humongous time to solve those problems. So that's why we are using some iterative methods for 2D solving 2D and 3D problem, and we cannot use TDMA and Gaussian elimination because they are very slow and it will take humongous time to solve the 2D and 3D problems. So what is Jacobi method? Jacobi method is we can understand it by example. It is very simple method actually. So in which we will do the iterations and we will find out the solution by finding the difference between the two iterations. If the error is reducing, means if the error is reducing, means the solution is converging. If it is converging, then only we can say we have found out the solution. So there is a way to find out that is my solution correct or not, is it is converging or not. or will it converge or not from the initial guess I am taking, from the equations I am solving. So I will discuss all of that and in the Jacobi method, and in the Gauss-Seidel method we will discuss about like how Gauss-Seidel method is a just an upgradation of the Jacobi method actually. So okay. So Jacobi method, so we can say there are just two equation and two unknown. Very simple equation I am taking, which is 2x1 plus x2. I am just repeating so that it will be clear. x1 plus 3x2 is equal to 30. So we can find out the solution of this equation in just by not doing any calculation, any of the calculation, we can find out the solution of this equation. What will be the solution? Solution will be 1 x1 is equal to 1 and x2 is equal to 4. Just put it and you will find out that this is the correct solution of this equation. But now we need to find out by some other method. We don't know the exact solution of the equation. Suppose any of the equation we don't know the exact method to solve that equation. So how we are going to find out that solution is just take this x1 here and 6 minus x2 will be here and by 2. So this is first equation. Just suppose first equation, then x2 will be 13 minus x1 by 3. It is the second equation. So just this I am taking it here. So I need to find out the exact solution or some solution for these equations. What I will do, I am just introducing a k term here. K is for time. Okay, just time 1 second, 2 seconds. These times I am introducing this k. So for the iteration, what I am doing is I will just take the value of the previous iteration and just put it here. I will just put it here and I will find out the next solution, and I will compare those two solutions. So it will be very clear. So x1 I will find out at time k by x2 at time k minus 1 means that from the previous time I will find the x1 value. Same with x2, 13 minus x1 from the previous time k minus 1 by 3. So this previous time and this time, this is the key point of this. So there is a question when we can say we have reached the solution. So this I will also discuss, which means the current value which I am getting for x1 or x2 minus the previous value which I got is equal to error, and if error is less than some convergence criteria, then I can say that my solution is achieved. So I can take any initial value. Sometimes it is given in the form of boundary conditions, sometimes it is not given. So just here I am just taking a value 0 for starting. For starting I just take x1 0 as 0. 0 means the time 0. At the initial time I am taking x1 and x2 as 0. So I will just put it here in this equation. So x2 from the previous time means x2, x1 at 1 time 1, x2 at 0 was the I am taking at 0. Then the value will come out as 3. I will just put it here 3. And here x1 I am putting from the previous time I am putting as 0. So 13 minus 0 by 3, which will come out as 4.333. So this is our first step, step 1. So I will just write it. This is our step 1 which I have done for solving the equation by Jacobi method.
Then for the step 2 what
I will do, I will just put this x2 from the time t1. So what I will do, I will just solve it. So I am just solving it here. x1 at time 1 or time 2, sorry, time 1 we have achieved. So time 2 is equal to 6 minus x1 at time 1 by 2. So what will be our value? 6 minus 4.333 by 2. What we will achieve? We will achieve this. We will achieve 0.834. this value at the step 2. So this is the step 2. And similarly I will put 3 here. So x2 at time 2, 13 minus 3, which is x2, x1 at 1 by 3. So 13 minus 3 by 3, which will be 3.333, which I have written here. So 3.333, 0.834. These values we have got. So what we will do, we will just calculate the error. Error will be 0.834 minus 3. This will be our error. So suppose it is 2.1 or something, and 3.333 minus 4.333, so it will be 1. So errors are huge. Now let's come to the another iteration, which is step 3. Step 3, what we will do, we will use these values. So x2 I will put it as 3.333. So 6 minus 3.333 by 2, which will come out as 1.334. Okay, 1.334, which is this value. And again 3 times 3, what will be our value? Time 2. So 13 minus 4.834 divided by 3. So what will be my value? It will be 4.056. So again I will calculate the error. Error will be 1.334 minus 0.8. So error is reduced. You can see it. So error is reducing here. So I can say that my solution is converging after iteration. Just for by the one iteration I can say my error is reducing. Then again I will do, because I want something error like 0.001 or something error. So what I will do,
again these value I will put.
I will again iterate. Again these value I will put in these equations. These value I will put in this equation. These equations. I will take some other these equations, and I will find out another step 4. Step 4 value again. So again you can see the error is reduced. Error is reduced here. Error is reduced again. So it is somewhat less than 1 here, and the 0.1 less than 0.1. Again I will do one iteration. Although I can say that I have achieved something or somewhere around my values, very near to my values, but again I will do some iteration and I will find out another value. So you can see it here. The error is very less, and I have reached the actual values which I proposed here, or which is the actual solution. I reached there. But
if I want to find
still, if I want to find some more accurate solution, I will again iterate it. Again iteration will give me very nearby value to the exact solution and very less error. Again I will do it, which will be this, and again I will do it, which will be 1.1 for the x1 and 3.997 or 998 for x2, which is 4 actually.
So this 1 and 4
this is 1. So this 1 and 4 I am getting from after 8 iterations. I am just getting it. Suppose I need to do it for n equations. What I will do? So we have find out, if we have an equation, we can write it in the form of ax is equal to b. So what I will do? I will do it here. A will be one matrix, x will be one column matrix, and b will be one column matrix. So A, and we will find out this A inverse here. And then x solution. But here what I am doing, I am just iterating these values to get the x value. So we can write these equation in the form of this, which is the summation of j is equal to 1 to n. J is one index, so a I j x j. So j is the index here in this direction, and I is the index in this direction. So I am writing the matrix in both the direction or matrix. So I have to have some point to write in both the directions. So I is this index, some index. So I is this index and j is this index. So I have the number of system of equations and di also here.
For solving that equation, only one at j is equal to I,
only one at j is equal to I will take it here.
Okay.
Okay.
I'm solving for one.
I'm solving for one line,
So
one row. So for one row,
I
xi
is equal to j. I am taking.
I is equal to j. I am taking that point. I am taking just and bi. So bi minus summation of j is equal to 1 to n, and j is not equal to I here. So that value we will just not include it here, and aij xj k minus 1, which is similar form of those equations which we have written. So there can be chances where the solution will not converge. So I will just discuss it, like where the solution will not converge. Okay, I have done something like that. So I will discuss those also. So what will happen, like suppose I have to reach this value. This is my exact solution. I have taken this or this A or this B as my initial guess.
So
So after iterations, I will reach to this point
for sure.
for sure. But suppose I have taken this as my initial value, and this curve is not going in this direction,
but it is going in this direction.
but it is going in this direction. So my value will never converge.
So this convergence
Will depend on different criteria. Means like we take some values in that. Suppose we are solving it in ANSYS or some code. ANSYS demand for some initial values to guess it or convergence criteria. And if suppose we are getting sometimes a diverse solution, then there may be some type of problem in the initial value. That I want to convey it from this plot.
There can be.
So you will be fundamentally very strong while solving the equation of the problem of CFT, when you know that where the problem will converge. And if it is not converging, what can be the reasonable reasons for not converging the problem? Okay. Then there can be faster algorithm or faster method to solve the equation. So then comes a Gauss-Seidel method, which is an improved version of Jacobi method. So Gauss-Seidel method is nothing but just an improved version, where what I am doing is whatever value I got in this iteration, I will just use that value in another solution, another equation solution. So the similar equation I have, okay, I have just make the same type of equation, a system of equations, where x1 at time k I am getting by x2 time k minus 1, which is from previous time step by 2. But for the x2 at time k, how I am finding this 13 minus x1 at time k only, means this value I will put it here. Instead of using, or in place of using x1 k minus 1, which I was using in the Jacobi method, I will use that k in place of k. I will use k minus 1. Oh, sorry, k minus 1. I will use k, which is this value direct from this iteration, so that my solution will be faster and it will converge fast. We will see the similar equation. We will solve by this method. We will see how that is converging it very fast as compared to. So we have solved this equation in 8 steps, and we found out the exact solution in 8 steps. I will just take similar initial guess. So x1 at 0 is equal to 0, x2 at 0 is equal to 0. These two initial guess I have
For
taken.
the iterations,
For the iterations, what I will do, I will just put. So I will take this and black. Okay. So let's take one value here, where x1 at time at time 1 is equal to 6 minus x2 at time 0 divided by 2. So this is our first step. So I have taken it 0. So it will be 3. So I will just put it as 3 here. Here 3. My first iteration. Then x2 at time 0, not at time 1, is equal to, here from here 13 minus x1 at time 1 only by 3. So this should be very clear. Okay, so I am just using this value which I just got from this iteration. So I will just put it here, 13 minus 3 by 3. Instead of using 0 here, which is my initial guess, I am using 3. So what will be my solution is 3.333.
This should be very clear.
So this should be very clear, and I will put this value 3.333 here in my table, which is my step 1. Okay, now let's come to the step 2. How we are going to convert this one. Step 2, what I am doing is x1 at time 2 is equal to 6 minus x2 at time 1 by 2, which is 6 minus x2. What is my x2 here? x2 is 3.33 by 2. So which will come out as 1.334, something like that. So x2 at 2, x1 at 2 is equal to 1.334, which I will put it here. Then let's come to the x2 solution. x2 at time 2 is equal to 13 minus x1 at time 2 by 3. So what is my x1 at time 2, which is 1.334. So I will put it, okay, just a second. 13 minus 1.334 divided by 3, which will come out as 3.889. So you can see the error is reduced in the first step.
I can say that my solution
is converging from the first step only. Okay. So this is done. So I will put these two terms here, which is actually my step 2. Now let's come to this one more step. I will show you how to do it. One more step, let me show you. So x1 at time 3 equal to 6 minus x2 at time 2 by 2, which is 3.881. 6 minus 3.889 by 2, which will come out as 1.056. So you can see the third step only we have come to near 1, and x2 at time 3 will be 13 minus x1 at time 3 only by 3. So this value 1.056 I will use, 1.056 by 3, which will come out as 3.981. Okay, I will just put it these value here, which will be my third step, which I have arrived here in around 5th step. So it will be my third step, and similarly I will do 4th step, which where you can see the error is reducing here, very less, 0.0 or something, 0.00 something, 0.000, 10 to the power minus 3. My error will be 10 to the power minus 3, and I can say these are my solution values. So error is reduced to 10 to the power, around 10 to the power minus 3, which is convergence criteria, I can say, and I can easily say that this is my solution, final solution, which is very near to 1 and 4 and accurate also.
I hope this is clear.
I hope this is clear. It should be very clear. These two methods are just done.
So we have seen
that this is a very fast convergence. Convergence is kind of, as compared to the Jacobi method, it is very fast. Almost twice the speed of the Jacobi method. But so how will we do it for n number of equations? Similar thing. Just we will divide those n number of equations into parts. Here, first part we will solve for this iteration only from the previous iteration value, and another part I will use that iteration value, the current iteration value of that solution, and I will put it in that part. So let me do it, or let me just explain it here. If you have any doubt, just let me know. From the assignment problem also you can ask. So for what we will do for n equations, n number of equation, or a system of equation, and there will be an unknown, obviously, an unknown and a number of equation. What we will do? So similar
like Jacobi method, Ax is equal to
Ax is equal to B kind of system of equation we will be having. That matrix, vector matrix, and this matrix. Okay. So how will we solve this? Just J is equal to 1 to n, addition A I J X J is equal to Bi. Similarly, I have this I in this direction, I in the J in this direction. So this will be my matrix, or I or J. This will be my matrix. So how will we do iteration?
At I,
at k time steps, I will just do summation of j is equal to 1 to I minus 1. Just look into it. It is not till n. It will be just till I minus 1. The value I am getting for this. So I will just do it for aij by aii. aii is this value, for I is equal to j. So I will just put it here. X j at k plus summation of j is equal to I plus 1 to 1. So I minus 1, then I plus 1. This should be the I at time step will be removed. There j is equal to I. This will be here, and I will just put j is equal to I plus 1 to n. So if you sum it totally, it will be j is equal to 1 to n. Just removing I is equal to j, which is similar to the previous. So aij here again,
and here
I plus 1 to n, and here this at this I am using the previous time step value, and here I am using current time step.
So this will be very clear when you try
to solve any other system of equation. That will be more clear. I can't show that. That will be like too much time taking thing. So you can try on your own and solve it.
So let's discuss about
the divergence criteria, or divergence. Then equations will be diverged. So that same equation, I will just change the order of the equation. So order, changing the order means I will just take one equation in the as I have taken for x2 I have taken the second equation, but now I will take for x2 first equation. was similar thing. I will just change the. So for x1 I will take this equation, x1 13 minus 3x2, this equation, equation 1. So similar equation I am taking, but just the order I am changing. And now you will see that how it is, it will just blow up. So x1 I am taking it here, 13 minus 3x2. So x2 k minus 1 from the previous time stuff I am taking. And here x2 6 minus 2x1 from the current terms. So this is Gauss seidel. Solution. Let's see how it is moving. I will just do a similar guess. Okay. So x1 at time 1 is equal to 13 minus x3 at time 0, which would be 13 minus 0, 13. Okay. x2 at time 1 is equal to 6 minus 2 into 13, which would be minus 20. This is my step 1 solution. Okay. This is I am just showing you to see that if it is converging or not, and if you have done something wrong, and taking the equation or taking the solution of equation or something like that, and there will be order of equations you will take wrongly, and sometimes initial guesses I have shown you that if you take it wrongly, then you can go into some other side, and the equation will not. Our goal is to solve the equation, nothing else. So now this 13 and 20 you have found this step. I will just put it here for the step 2. x2, what is my x2? Minus 20. Okay. 60 plus 13 is 73. So I have found out it 73 then. 2 at 2 is 6 minus 2 into 73, which is 146 minus 6, which is minus 140. I will just put it here. These values I will put it here. 140. Again I will solve this equation. I will find that it's these values. So I can say that my values are blowing up. This x1, x2 value. This is not possible. One thing is 473 minus 13. The error is 60. Here minus 407 minus 73, which is 480 minus 4. So error is increasing from 760 to 480. My value of error is increased so high. So I can say that my solution is blowing up. It is called as blowing up of solution, and it is diverging. For in other sense, it is diverging. My solution is diverging, means error is increasing exponentially by that time. So a solution will blow up. The solution has done. These are the two terms which they will use for this. Suppose you have given two equations or some number of equations. How will you see that there can be some kind of there should be some type of criteria from which by just looking at the equations we can say that it is converging. It will converge, or it will not converge. It will diverge. So there will be there is a criteria, but it is not a necessary criteria. It is just a, you can say, it is not a necessary condition. It is not a necessary condition, but just a you can judge by this solution. It can. So if we have a discretized equation of the form AP, TP, and sigma A and B, T and B plus B. So let me just do it. P is current grid point value, present value,
and NB is neighbor value.
And NB is neighbor values.
So sufficient condition is
So sufficient
not
condition is
fulfilling
it
or
is not a fulfilling or
compulsory
you can
condition.
say
But
compulsory condition,
it is
but means if it is
just
uh, just what I can say, let me
if it
just
is
think.
just
So if it is just
so it
the
is a
satisfying,
sufficient condition only.
so
But
it is a
not
sufficient
just
condition
satisfying,
only,
you can
but
just say
not if it is
that
satisfying you can just say
it will
that
convert.
it will converge.
Let me be clear,
So
it is not a
let
necessary
me be clear, it is not a necessary condition.
there is
Means
no
if it is, there is no
necessity that it will not
necessity that it will not diverge or it
that
will.
should be very clear.
So that should be very clear.
So
So
here,
this A and B will come here.
absolute value of A and B
Absolute
comes
value of A and B will come here. So let me be clear about this absolute value, and summation of those neighboring points will be here. Divided by the present gate point value should be less than equal to 1
and
for all equation, and for at least one equation it should be less than 1. So all can't be equal to 1. There should be some equation which is 1 equal to 1. So at least one equation should be there.
So the thing I was telling,
So the thing I was telling, I have written it here. This is not a necessary condition but a sufficient condition. So let's see for our
what is so
our equation what is.
okay.
So this is okay. So let me make it okay.
So what is our
What is our
A and B
A and B here? A and B is
and what is our AP?
and what is our AP? AP is 1.
3 by 1.
So 3 by 1 is greater than 1. So there is no condition which is first condition is not satisfying. So it will not converge as we are seeing. And here the value is 2 again, 2 by 1, which is again greater than 1. The two condition are not satisfying. So I can say the value will diverge, and which we have seen the value is diverge. So this Scarborough criteria is a criteria from which you can see that will it converge or not. So let's see for our previous equation. So here our A and B value is 1 by 2 divided by A P value is 1. So it is less than 1. And so second equation and first second condition and first condition both are satisfying here. Then 1 by 3 is for this equation, and divided by 1, which is 1 by 3, which is again less than 1. So for both the equations it is satisfying less than 1 criteria. So which is convergent. So Scarborough criteria, just look into it. Now I will cover about line by line TDM, which is last method for solving the system of equation. Okay. So let me just go to it. What we have just a thing. This is like so here we have covered this direct method and iterative method, Jacobi Gauss-Seidel, and last we are in the iterative method line by line TDM I am discussing that, and I will just introduce you to finite volume method. So I am just making it very clear where I am going. So Gauss-Seidel method, I can say that it is faster than Jacobi, but it is still very slow.
There are faster
iterative methods such as line by line TDM. What we will do, we will consider a 2D problem. Just consider a 2D problem. Here I am making some grids, okay, for finite difference. So there will be a grid points here,
So these grid points I have shown it like I j minus 1, I plus 1 j. So maybe it is not visible. Let me write it again fast. So I comma j minus 1, I minus 1 comma j. So I plus 1 comma j. So I j minus 1. I comma j plus 1, I comma j. So these sum values are there, and typically the discretized equation for 2D problem is of this form. So let's see, like what will be the form of discretized equation. Aij, Tij. Tij is some value of temperature here for any value. So Aij, Tij is equal to the summation of all these. So Ti plus 1, Ti plus 1j, which A is some constant which is coming, or some other value which is coming. Similarly in the other terms also, and Dij is another term. So this is just an equation which we are representing by negating value. We can use TDMA along one direction, like a 1D problem, by taking old iteration values as known values for other iteration. What it is trying to say is that I will just solve in this direction, like I have solved in the 1D, or in this direction, like I have solved in the 1D TDMA problem. By just moving in one direction, again coming and iterating, or not iterating, and again coming and eliminating in the reverse direction. I will just do it in this direction or this direction. From the previous values which I have, the previous values of time, I will have the next value just by solving in one direction. So in one direction I will solve, again I will sweep in this direction, and again I will move forward. That will be clear. For example, for I direction values, so there are some values from so Tij, I plus 1 I am using, Ti plus 1, and I am minus 1 I am using. So in the I plus 1, I minus 1, so I am using this direction. I will use these values. So these values are from coming from the previous k minus 1. K minus 1 is there, you can see. This is very important. Aij plus 1, then Tij plus 1. For k minus 1 value I have used, k minus 1 value I have used, and Dij. So these are known to us from the previous iterations, or from the 1D condition, and we will find out these equation. We will solve it by TDMA method in one direction, then I will sweep it. So k minus 1 is already known. So for entire I direction is solved in one iteration. So for one direction it is solved in just one iteration. Then we will move the calculation to the next line. Suppose I am using this line for this line, I will just move it for the next line. And this is called as sweeping. What is sweeping? Sweeping, okay, sweeping, I will just move into the next line, which is called sweeping. So sweeping will be preferred in those directions. Suppose my flow is happening from here to here, so I will sweep from here to here. So this is more suitable as compared to sweeping from here to here. Then alternating the sweeping direction, accelerate the convergence. Oh shit. Alternating the sweeping direction, accelerate convergence. So what we will do, like we are converging in this, accelerating in this direction. Oh sorry, we are sweeping in this direction. Then what we will do, we will just sweep in this direction. Okay. Again, iterate in this direction, and then sweep in this. So this will also improve the convergence, or accelerate the convergence, and boundary information is brought to the interior quickly. So boundary condition will be applied here quickly, just this. So instead of taking horizontal line, we will just take vertical line. So it is very counterintuitive, or intuitive. Along the line, in the transverse direction, the boundary information is passed at once. Okay, so this is clear. So from obviously into down will result in much faster conversion. So by that I can say we have concluded all the iterative and direct method. I will just cover some part of the finite. I just want to cover it so that just for an introduction. So for finite difference, we have used the differential forms, and we have discretized it, and we have used we have. Oh, Arun, are you asking something?
Yes, sir.
Okay, just a second. Now you can ask.
In the last equation for line to
Okay.
line TDMA,
Hmm.
that AP ATIJ. How to solve this equation by Gauss setup?
Which question? Well,
TIJ is equal to TIJ.
this equation. Okay.
The above one, the upper one,
This
the rest.
both are same actually. So by Gauss Seidel, you will just take this. This is the same form as. Okay, let me come to that equation. So these are the same form as. Yeah, just a second. Just a second. So here I will use this n number of equation by n unknown. Okay. So here also I have equation n unknown.
Just put these terms.
Just put these terms. Okay, I will try to make it more clear. Now I have very less time, so I think I have not made it very clear to you. Gauss Seidel.
Actually, in assignment 7, there is a term for stream function psi. So I solved it by over relaxation method. It is similar to Gauss Seidel, I think, because we are using only relaxation factor f. But
Yes.
my solution is not converging. It is, I mean, after iteration 3 and 4, it is producing infinity. So I don't know where I am going wrong, and I have no idea.
Can you just repeat the question? What you are solving and there it
In
is.
equation in assignment 7, we are solving the equation by streamline vorticity function. So in that
Understood.
assignment, we are having a equation for a streamline psi. The similar equation which you have written here, Aij, Tij. The similar
Understood.
equation in stream function. But I'm using over relaxation method, but my solution is diverging after iteration 3 and 4. So I don't know where I'm doing the wrong.
Check it by
Over relaxation you are using. So you just check it by your equation. Maybe the order is different. You just check it by this Scarborough criteria which I just discussed. Can you just check it by Scarborough criteria that you have taken the right order of the equation? Or you can change the order of it.
Yes, I will check.
You check it. Like it is a summation of neighboring points here. And so Scarborough criteria, just check it. If you are solving by that over relaxation method.
We will discuss it in
We will discuss it in next class.
Thank you for asking this.
Thank you for asking this. And so I will just discuss this finite volume in the next class. Okay. So some other doubts, Arun?
No, sir. I have only this doubt because my solution was not converging. So I'm still trying, but the deadline is over. So I got 0 marks, but I'm still trying to get the right answer.
Oh, that's not an issue. In the exam, it may be.
Yeah, because I should know the programming. The marks is not important as of now.
Are you comfortable with
Exactly. So, are you comfortable with the code writing, or
Yeah,
should I discuss it from the next
Fortran
class?
language. I am writing code in Fortran language.
And that's good.
I mean, I'm not like expert, but I just learn.
You don't have to.
I just learned how to make program in Fortran. So I solved assignment 5th and 6th in the same Fortran. I got the right answer, but in this assignment 7, I'm struggling because my answer is my solution is not converging.
Discuss about the order.
So I
I will
just
check it.
the order. Okay. So maybe that there you are going wrong.
Yes, sir.
Just take different equations and you will get it.
Okay, thank you.
Thank you. Thank you, Arun. Thank you, Arun. Okay, so let me discuss briefly about finite volume so that I will conclude it in the next class. So in the finite volume, you have learned about the finite volume method. Am I correct?
Yes, sir.
Okay, so finite volume, so it is just using the integral form of the conservation equation, which is and domain is divided into finite number of control volumes.
I have just divided.
So I have just divided, or we can say it as making of discretization in a grid form.
So
So
here I'm not using these points.
here I'm not using these
I will just
points
use
value. I will just use a control volume, and center will be my grid point, or center, or you can say some point will be there, which I will say it as a grid point when I'm dividing it into finite volume or control volume in a domain.
So
And
this control volume
so
is
this
represented
control
by
volume is represented by this point. Means all the values of temperature, pressure, and every variable will be represented here at this point, which is called as grid point,
which is
and which is pointed at the centroid, which is here it is. This is centroid. If it is this type, this will be center of this or centroid of this of the control. Then properties such as TP, temperature, pressure are defined at the each grid point. So
what I want to discuss is
what I want to discuss is the conservation equation has two forms. So many of you must have understood this, but some of you who are watching this recording are still struggling with the differential and equation integral form. So this differential form when we will use it is valid for a point, but integral form is valid for a larger group. That's why for finite volume method we will use integral form. Okay, finite volume confirms that method confirms that conservation. So all the conservations like energy conservation and mass conservation will be applicable directly while directly applicable in the finite volume method, but it was not in the finite difference. So
okay.
Let me stop it here, and this other things I will discuss in the next class, and some of the doubts. Arun, you asked this doubt. I will try to discuss in the next class.
Okay, thank you.
Okay. Thank you all. Thank you all of you. I'm just leaving this.